Hi, we're Zeke and Niles, and today we'll be talking about divisibility rules with modular arithmetic.
Okay, so here we have 12 blocks, and we can count these blocks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But let's say we wanted to count these blocks not by ones, we wanted to count them a different way, a little bit faster. Well, we could try counting by 2. Here's one group of 2, a second group of 2, a third, a fourth, a fifth, and a sixth. Now we have two. Now we have 6 groups of 2. Well, we could also try counting these groups by 3. Here we have one group of 3, 2 groups of 3, 3 groups of 3, 4 groups of 3. What if we wanted to count this by a number even bigger than 3, but instead of 4, let's skip and let's go to 5. Here we have one group of 5, 2 groups of 5. Well, we have two blocks left over. We can't count by 5 again. So, what does it mean for 12 to be divisible by some other number? Okay, so in our first example, we saw that when we counted off by 2s, there were no blocks left over. And when we counted off by 3s, there were no blocks left over. But then when we tried to count by 5, there were a couple blocks left over. 2 and 3 are divisible. 12 is divisible by 2 and 3 because we were able to count 12 evenly by 2 and 3. But 12 is not divisible by 5 because when we tried to count by 5, we had 2 blocks remaining. Okay, so before we showed that 12 is divisible by 2, but what if we had a really, really big number, like and what if we wanted to know if that number is divisible by 2? It doesn't make sense to try and count by 2s until we get to the end of this number to find out if it is divisible by 2. But there are actually some pretty neat divisibility rules for certain numbers. So just looking at this number, I already know that it's divisible by 2 because the last digit is 8. If the last digit of a number is divisible by 2, then that number is divisible by 2. So, and if a number ends in 2, 4, 6, or 8, it is divisible by 2, and if it ends in 0, it is also divisible by 2. Okay, so we showed earlier when we were counting by 12s that when we were counting the number 12, that when we tried to count by 5, there were 2 pieces remaining. So therefore, 12 is not divisible by 5. What if we wanted to know if this number is divisible by 5? Similarly to 2, we can tell if a number is divisible by 5 by checking the last digit. If the last digit is a 0 or a 5, we know that number is divisible by 5. So this number is not divisible by 5 because the last digit is an 8. What if we wanted to know if this number is divisible by 3? The divisibility rule for the number 3 is actually really cool. If we sum up the digits of this number, 37 plus 25 equals 62. And then 6 plus 2 equals 8. So this number is not divisible by 3. So how did I do this? The divisibility rule for 3 is if the digits add up to a multiple of 3, if the sum of the digits is divisible by 3, the number is divisible by 3. So when I summed all these digits, I got 62. And rather than checking, 62 is not divisible by 3, so we know that this number is not divisible by 3. But if you didn't know if 62 is divisible by 3 or not, we could just apply the rule again and sum the digits of 62, and then sum of the digits of 62 is 8, so we know that this number is not divisible by 3. Okay, so in our previous example, we showed that when we were counting the number 12 by 5, we had 2 groups of 5, but then we had 2 left over. So we could represent 12 as 2 times 5 plus 2. And we call this number that's left over our remainder. So when we have a number and we try to divide it by another number, if it doesn't go in evenly, we call what's left over our remainder. Or another way of saying this is we could say that 12 is congruent to 2 mod 5. Okay, let's say we have some number A, and we divide it by some number B. We can say that A is congruent to R mod B. A cool property of divisibility is that A to the K is congruent to R to the K mod B. And understanding this is very important to understanding why our divisibility rules work.
So from the last part, we saw that if we can write A is congruent to R mod B, then we can also write A to the K is congruent to R to the K mod B for all K in the positive integers. So if we have some number, some bigger number A, and we're trying to divide by a smaller number B, and that would give us a remainder of R, then we also know that if we take this number A, raise it to a certain exponent, and then try to divide by B again, the remainder is going to be the original remainder to the exact same exponent. So how can this be applied to our divisibility of 3 rule? Remember, the divisibility of 3 is if the sum of the digits is divisible by 3, then so is the whole number. Remember that the numbers we're working with right now are in base 10. So for example, if I have some number a, b, c, where a, b, and c are the digits of the number, this can be expressed as a times 10 squared plus b times 10 to the first plus c times 10 to the 0th. We can say that when we have a number 10 and we divide by 3, we have a remainder of 1. So we have that 10 is congruent to 1 mod 3, and thus 10 to the k is also congruent to 1 mod 3 for any positive integer k. Thus, when we write out our expanded form of ABC, and we are doing modular arithmetic mod 3, then these 10s and their powers turn to 1s, and the sum of the coefficients of the powers of 10 becomes congruent to the ABC number we originally had. Thus, if 3 is divisible by the sum a plus b plus c, then 3 is divisible of ABC. We want to know, is this generalizable? For example, can we say for any number n, does that number divide some other number, big N? And specifically, we want to be using the same rule. We want to see in what cases do the sum of the digits give us the divisibility rule. So remember from above, we want the form where the digits in expanded form, in this case we're writing the digits as xk minus 1, all the way down to x naught for a k digit number, or a k plus 1 digit number. We want the form that this number is congruent to just the sum of its digits mod n for some number n that we're dividing by. Well, remember that we were writing originally in base 10, but what if we're not writing in base 10? What if these digits xk and so forth don't represent base 10 digits, but instead represent some arbitrary base b? Well then, we know from above that if our b is congruent to 1 mod n, then our divisibility rule will hold, such that if the sum of the digits xk minus 1 through x naught, and base b is congruent or is divisible by n, then the number itself in every base is divisible by n. In other words, to check if some big N, a natural number, is divisible by little n less than it, we can define big N in the base of little n plus 1 with the digits xk, xk minus 1, and x naught. Remember, this number here is in base n plus 1. Then, to check if our number big N is divisible by little n, we take the sum of the digits in base n plus 1 and check if little n divides that sum. If so, then we can say little n divides big N. Let's check an example of this. We want to know if 13 divides 611. So first, since we're dealing with dividing by 13, we want the modular regime we're in to be mod 14, so mod 13 plus 1. So if we're going to express the number 611 in base 14, we can write it as 3 times 14 squared plus 1 times 14 to the first plus 9 times 14 to the 0th, giving us 319 in base 14. Now, if we take the digits 3, 1, and 9, and we sum them up, we find that we get 13, which is congruent to 0 mod 13. In other words, 13 divides 13, and so 13 also divides 611.